So you need to find the moment of force above F. Right? So what you need to do is you need to find the perpendicular distance from the pivot. If I create this line, and this is the pivot, right?
Yes.
Isn't this distance and this force perpendicular here?
Yes, yes.
So it should be F into OY. V should be the answer.
Oh,
Okay, so basically what you need to look for is you need to look for the force, and from the
Stretch it.
pivot, yeah, just find anywhere a line that's perpendicular to the force. Right, let's continue. I just wanted a clarification. The other what is it? DPS, right? You guys have materials in your exam, right? Like this deformation. But when is the exam? This Friday? Saturday. I'll try to wrap it up because some of you wanted the notes on deformation. I'm not done with it yet. So right, so just quick reminder of what it is that we did last class. I'll be asking you some questions. So we did the energy interaction of springs. So when you stretch a spring, the area under the graph represents the elastic potential energy, right? And when you stretch it, you provide it work, and it stores some of the energy out there. Does it store all the energy you provide? No, right? Remember that the work done is actually force into distance, but the energy stored is not force into distance, right? It's actually half force into distance, right? So that's the area under the graph. I haven't seen them ask yet why is it half, okay? But it's something that should be there because so the other half of the energy is due to the resistive forces provided by the spring. So when you're trying to pull a spring, it's not a free movement. There's an opposition to it, okay? So that's why some of the energy is wasted to overcome. I provided that here, okay? Half of the work is done in stretching the spring. The other one is, to overcome the forces. Now, once you stretch it within the elastic limit and you unstretch it, right, you will notice that the amount of energy that you get back is the same. Why? Because the spring didn't deform. So if the spring doesn't deform, there's no bond breaking, there's no permanent energy loss. So jeta hoy is the amount of energy you gave in is the same amount of energy that goes out, right? So in and out, loading, unloading, that's all fine. But once you cross the elastic limit, that's where our syllabus actually is more concerned. So once you go beyond the elastic limit, what you find is this whole thing is the amount of energy you had given. But the orange part represents the amount of energy that you actually got back. So you'll find that the yellow part is missing. It doesn't come back actually. And that yellow part is the amount of energy retained by the spring. And why did the spring keep that energy back for itself? Because when you go beyond the elastic limit, what are you doing? Breaking bonds. And if you break your bonds, that energy is non-reversible. It's permanently gone, right? And therefore that energy can't be retained. You only get back the amount that is available, right? Is all of your energy needed to break the bonds? No, right? Otherwise, you get my point. Like if the entire amount of energy was needed to break the bonds, right? It turns out whenever you stretch a spring, right, and you deform it at a point into back forward, right? Because it's not permanently fully deformed, right? So that's the reason why you do get back some of the energy here. However, you definitely don't get back all the energy. And that's the energy retained as internal energy. What's the evidence of the energy being retained? You'll find that the material is what than before. Longer, yes, and deformed, yes. It gets warmer. It gets converted to internal energy, and internal energy is what makes objects become higher in temperature. Okay, so if you keep doing this multiple times, your material will get very warm because the energy is going into the bonds, right? So yeah, that's what we did last class. It's a different topic. So I just want to check if we have covered everything here or not. So 6.2 they start, but see if you have anything here or not. Okay, understand elastic deformation, plastic deformation, elastic. I think we have covered these, right? Elastic deformation, apply force, stretches, remove more, roll back. Plastic deformation, apply force, stretches, remove force, does not completely go back. If you say it doesn't go back, that's wrong. It doesn't go back, not completely. I think elastic the point to show elastic behavior, right? Understanding the graph is work you did that. Elastic potential energy is in the linear proportionality of the graph. So we straight line and our bit and form a half x or half a square. I even think from it class a square term f is equal to ax. So half fx over there, f is equal to k what is the number? K squared, right? So yeah, that is elastic behavior. Asking about different from this. Okay, so that's what I want to build the line here. This is done. So what are we done with? We're done with springs. We're done with the behavior of springs. You can add charts. I'm not really sure. Did in the syllabus or not? I mean, I think it's